Okay, so we learned about, in the last video, we learned about capacitors and time constants. In this video, we want to talk about how we can incorporate that capacitor into a rectifier circuit like this one here and this half-wave rectifier here, and see how that helps us to achieve that constant DC output. So again, let's just look at the output of this half-wave rectifier. Remember, it selects only the positive parts of the input sinusoid to appear at the output. Okay, so this is V out, and we want to smooth that off to a DC constant value. That's time there. Okay, and how we do that is we actually introduce a capacitor into the circuit here. Okay, so we place the capacitor parallel to the load. Okay, the load resistance there. And what effect does that have on this output graph that we observe? Well, when we have a positive voltage, we'll have this positive voltage appearing across both the capacitor and the resistor. Okay, and during these positive peaks here, this capacitor is going to charge up. Remember, we saw this graph of a charging capacitor. Okay, so the capacitor will charge when there's a positive voltage applied to it. That is, it will build up a collection of positive charge on this plate here and negative charge on this plate here. Okay, it's storing that charge in the plates. But then, when this applied voltage disappears, okay, in this period, these parts of the graph here, there's not going to be that electromotive force pushing that charge onto this plate anymore, okay? And it's going to want to get away. It's going to repel itself, so the negative charges will repel the other negative charges and push them away from this plate here. Positive charges will repel the other positive charges. So what happens is we end up with a flow of conventional current back off the capacitor, okay? So it'll be flowing out of the capacitor in this direction. Now, where's it going to go? Is it going to go this way, or is it going to go that way? No, the conventional current can't flow through the diode because that blocks current flowing in that direction. So it's going to end up flowing off the plates and around and through the load, okay, and across the load. So while we had these positive sections, we had a positive voltage across here, and now that that's been taken away in this section here, we're going to still have current flowing through the load, and we're still going to have that positive voltage, therefore, appearing across the load, and it's going to discharge the capacitor according to this sort of discharge pattern that we saw in the last video. Okay, so it'll discharge something like this. Now we know that how fast and how slow that it discharges is dependent upon the time constant, and ideally we want to minimize this amount of discharge in one of those periods. We call the measure of how far the capacitor and how far the voltage drops in one period the ripple voltage, V ripple. And there are different things that we can do to minimize that, and I'm going to talk about that in the next section of the video. Okay, so this is example 8.3b from the textbook, page 304, I think, and they provide us with this circuit diagram. We can just identify quickly the parts of the circuit diagram. This is a sinusoidal, an alternating current source, okay, and we're actually told that that is the mains power supply, so that'll be 240 volts. This is a transformer, okay. These two coils, we can tell that's a transformer from the two coils. These lines in the middle represent the core of the transformer. It's not important that you know what that is at this stage. This is a diode, and there's only one diode, so in this circuit this is going to be a half-wave rectifier. We should tell straight away from the single diode. This is a resistor. This is the resistance load, and we're told that that's 500 ohms. And here's a capacitor, okay, and this is a smoothing capacitor because it's in parallel with the resistance, like the one that I showed you before. And also we should note that it doesn't matter which side of the resistor we put that capacitor on, okay, it'll still have the same effect as long as it's in parallel. And there's also a switch here which allows us to connect and disconnect that capacitor. The capacitance is 100 microfarads, and we should remember that the prefix micro is 10 to the minus 6. So the first thing that they want us to do is sketch and they want us to sketch this voltage between X and Y when this switch is open, so when the capacitor is not connected in the circuit. And just from our understanding of how half-wave rectifiers work, we should be able to sketch that it's going to be something like this, okay? Where we'll end up with just the positive peaks. There's no smoothing yet, the capacitor's not disconnected, so we won't smooth these peaks off, it's just the individual peaks, okay? A little bit more information that we could put on there perhaps would be the period T of that. This is being time on this axis and this being voltage on this axis, Vxy. The time, the period of this signal, how would we find that out? Well, we know that this is a main source and the period will be the same even after it's gone through the transformers. The frequency of mains, F main, equals 50 Hertz. And we know that period equals 1 over 50 equals 0.02 seconds or 20 milliseconds. Okay, so the period there is going to be 20 milliseconds. Excuse me. The second thing that they ask us to do is to calculate the time constant of the... Oh no, so the second thing that they ask us to do is to explain how this output will be affected when this switch is closed, so when that capacitor is included in the circuit. And just from what we've seen, we should be able to make a couple of points that the capacitor will charge when the input voltage is high, okay? In these parts here, when input voltage is high, and discharge to smooth the output voltage when V in is low. Okay, so when in these sections here, the capacitor will slowly discharge and smooth that output. Now, they ask us to calculate the time constant of discharge of this capacitor. Okay, so it'll discharge through this resistor, and we know the formula tau, time constant, equals RC. Okay, and so that'll be 500 times 100. Now, 100 microfarads is times 10 to the minus 6 farads equals 0.05 seconds or 50 milliseconds. Okay, so the time constant is 50 milliseconds. Now remember, the time constant is how long it takes for the capacitor to discharge 66% of its value, or to drop to 33%. And so it will take 50 milliseconds for the capacitor to lose that amount of value. The period of this signal is 20 milliseconds. And we synthesize those two bits of information to make an estimate of what the smoothed signal will look like. Okay. Now, because we know it takes 5 time constants to discharge completely, okay, and we're not going to reach that in 20 milliseconds, so it's not going to have time to discharge completely. It's not going to go down to there, but it will discharge some, okay, because the time constant is of the same order as the period. So it's not going to flatten out completely. It's going to be somewhere in the middle. Okay, so the discharge, the smooth signal is going to look something like that. So let's try and sketch the final version of that. It'll charge up, it'll discharge a bit, it'll charge up again, that last one's pretty dodgy, charge up again, and so on. And again, the period of this is still going to be the period of the ripple voltage. This is the ripple voltage here. Period of the ripple voltage is still going to be 20 milliseconds. The final thing they ask us to do is to make an assessment of how could we change this circuit to smooth it out more. Well, if we increase the time constant, the capacitor will discharge more slowly, so we could increase the resistance, okay, of the load. That might not always be an option because the load might be an appliance or something that we don't have any control over if we're just building the power supply. But the thing that we can do is we can increase the capacitance here. So we can certainly increase the capacitance, or if we have the option, increase the load.